There's a machine out there, right now, moving through the darkness between stars. It has no fuel left to burn, no camera to see with, no way to stop. And yet, it is still talking to us. Every day, engineers at NASA sit down and listen to a whisper, traveling across 25 billion kilometers of empty space. A signal so faint, it arrives with less power than a single grain of sand falling onto your palm. Most people have never asked the question that keeps scientists awake at night. What did Voyager 1 see before it went blind? And why did it leave everyone speechless? Something left Earth on September 5th, 1977. It was not much to look at. A machine roughly the size of a small car, built with technology that today's smartphones would embarrass without effort. The processors on board had less computing power than a digital wristwatch. The memory it carried could not store a single modern photograph. And yet, NASA pointed this machine at the darkness and let it go. Nobody at the time could have fully grasped what they were releasing into the universe. Nobody understood that this small, humble spacecraft would one day cross a boundary no human-made object had ever crossed, transmit data that would rewrite textbooks and capture images so philosophically devastating that scientists struggled to speak after seeing them. This is not a story about a space probe. This is a story about the moment humanity looked at itself from the outside and could not look away. But here's where it gets strange. The final images Voyager 1 ever took were not of some distant alien world. They were not of a black hole or a supernova. The final images it captured, before its cameras were shut off forever, were of us. And when scientists processed those images and held them up to the light, something happened in those rooms at NASA's Jet Propulsion Laboratory that no press release ever fully captured. The silence that fell over those scientists was not the silence of confusion. It was the silence of people confronting something they were not emotionally prepared to understand. Think about what that means. The most advanced minds on the planet, people who had spent careers calculating the precise mathematics of the cosmos, people who could describe the magnetic field lines of Jupiter with the same ease others describe the weather, those people went quiet, not because the image was technically impressive, because it was not. The image was terrible by any photographic standard. It showed a grainy, blurry smear of light. A tiny fragment of color caught inside a sunbeam, almost accidental in its composition. It was taken on February 14th, 1990, at 4:48 in the morning, Greenwich Mean Time. Voyager 1 was already past Neptune. It had been traveling for over 12 years, and NASA engineers made a decision: turn the spacecraft around one final time, point its aging cameras back toward where it came from, and take a picture of home. What they got was a photograph of Earth reduced to 0.12 pixels. Read that again. Not a pixel, not even one full pixel. Earth, like with its 7 billion people, its oceans, its mountains, its centuries of wars and civilizations and love and catastrophe, appeared as 12/100ths of a single pixel, suspended inside a scattered ray of sunlight against an infinite black void. And here is what nobody tells you about that moment. The cameras on Voyager 1 had to be manually aimed at Earth, and the precision required was extraordinary, because from that distance, Earth was nearly impossible to distinguish from the background noise of space. There were people at NASA who argued it was not worth doing. There were engineers who said the power required to take those photos could compromise the mission. The man who pushed hardest to take the image against institutional resistance, against bureaucratic caution, was Carl Sagan. He believed that science alone was not enough, that humanity needed to see itself from the outside, even once, to understand something it could not understand any other way. He was right, but the consequences of being right turned out to be more profound than even he anticipated. The 60 images taken that day became known collectively as the family portrait of the solar system. For the first time in human history, a spacecraft had turned around and photographed nearly all of the planets from a vantage point beyond the edge of what we consider our neighborhood. 6 planets were visible. Mercury was too close to the sun to capture. Mars was too faint. But Neptune, Uranus, Saturn, Jupiter, Venus, and Earth, they all appeared. Not as worlds, not as places, as individual points of light or fractions of points of light, hanging in an absolute dark that had no end in any direction. But here's where the story shifts into something darker. 34 minutes after those images were taken, 34 minutes, Voyager 1's cameras were switched off, permanently. Not because they failed, not because they broke, because the people running the mission made a calculated, deliberate decision to kill the cameras in order to preserve power for the instruments that mattered more. The spacecraft still had decades of travel ahead. It would need every watt of electrical power its nuclear generators could provide. Cameras, in the cold arithmetic of deep space mission planning, were a luxury. And so, in the early morning hours of February 14th, 1990, humanity took its last look back. The cameras went dark, They have never been turned on since. They never will be again. What most people are not seeing is this: that decision was not a failure. It was a choice. And understanding that choice, understanding why NASA engineers were willing to blind their own spacecraft, unlocks something important about what Voyager 1 was truly built to do. It was not built to take photographs. It was built to feel, to sense, to probe, to measure things invisible to any camera. The magnetic fields, the plasma waves, the charged particles streaming through the space between stars. And in that invisible work, hidden from any photograph, Voyager 1 has made discoveries so unsettling that scientists are still processing their implications today. In August of 2012, after 35 years of travel, Voyager 1 crossed the heliopause. This is the boundary, the actual physical edge, where the sun's influence ends and interstellar space begins. It is the shoreline, as NASA's own project manager, Susie Dodd, would later describe it, between the ocean of our solar system and the uncharted continent of the galaxy beyond. No human object had ever crossed it. No instrument had ever sampled what lay on the other side. And when Voyager 1 went through that boundary, it found something that nobody had predicted. The magnetic field did not change direction. Every theoretical model, every simulation, every scientific consensus had assumed that when you crossed from the solar wind into interstellar space, the magnetic field orientation would shift dramatically. It would have to, because you are crossing from one domain of magnetic influence into another. But it didn't. The field lines on both sides of the heliopause were aligned in almost the same direction. Scientists stared at the data. They ran the numbers again. They questioned their instruments. They questioned their models. And eventually, they had to acknowledge what the data was telling them, that interstellar space does not begin where we thought it did. Or rather, it does not behave the way we assumed it would. According to informed sources within the astrophysics community, this single discovery quietly dismantled a foundational assumption that had been baked into heliospheric science for decades. The boundary between our solar system and the galaxy is not a clean wall. It is not a door. It is a permeable, complex, dynamically shifting zone that allows particles and magnetic influences to leak through in both directions. The heliosphere does not end sharply. It bleeds. When Voyager 1 crossed the heliopause, it also discovered something on the other side that should not have been there. The temperature outside the boundary was expected to be cold, brutally, cosmically cold. The interstellar medium was theorized to be a sparse, cold, relatively quiet environment. What Voyager 1's instruments measured instead was a plasma wall, a region of superheated particles sitting just outside the heliopause, registering temperatures of approximately 50,000 Kelvin, 50,000 degrees, hotter than the key, surface of the sun in some comparisons. This thermal barrier, this blazing wall at the edge of our solar system, had not appeared in any major model. It was not predicted. It was not expected. And its presence raises a question that planetary scientists are still wrestling with. If our heliosphere is pushing against something that hot on the outside, what does that tell us about the structure of the interstellar medium itself? The real story is that Voyager 1, by simply surviving long enough to reach that boundary, exposed enormous gaps in our understanding of where we actually live in this galaxy. We do not fully understand the shape of our own cosmic neighborhood. We do not fully understand what protects us from the radiation streaming in from the rest of the universe. And Voyager 1, with its instruments built in the early 1970s, using technology that is now genuinely antique, is the only machine that has ever directly sampled what lies beyond that boundary. There is no other spacecraft there. There is no backup. There is no second opinion from a fresher instrument. All the data we have ever directly collected from interstellar space has come from two spacecraft, Voyager 1 and its twin, Voyager 2, which crossed the heliopause 6 years later in 2018. Together, they are humanity's only hands reaching into the space between stars, and both of them are running out of power. According to NASA's April 2026 updates, engineers at the Jet Propulsion Laboratory recently made a decision that would have seemed unthinkable years ago. They shut down the low-energy charged particle experiment, known as the LECP, aboard Voyager 1. This was not a casual decision. Scientists and engineers had spent years developing a careful, prioritized shutdown plan, a triage protocol for a dying spacecraft, because Voyager 1's nuclear power supply, a plutonium-based radioactive thermoelectric generator, loses a small fraction of its electrical output every single year. 7 of the original 10 scientific instruments have already been turned off. The LECP was the 8th. Each deactivation is a small funeral. Each one marks another piece of humanity's most distant outpost going permanently dark. What remains operational on Voyager 1 are the instruments capable of measuring magnetic fields, plasma waves, and cosmic ray activity. These are the instruments NASA has decided are most valuable, because they are the only ones telling us anything about the actual structure of the space Voyager is passing through, And even as the spacecraft loses capabilities piece by piece, those remaining instruments are sending back data that continues to surprise. Recent scientific papers published in 2025 and 2026, drawing on Voyager 1's magnetometer data from the previous several years, have revealed that the magnetic field in the very local interstellar medium is not stable. It fluctuates, it shifts. Between 2024 and 2025, researchers tracking Voyager 1's magnetic field readings documented the field strength dropping, then rising, then stabilizing, behavior consistent with a dynamic, turbulent interstellar environment that was perturbed by solar activity years earlier. The shockwaves sent out by solar eruptions on our sun, traveling outward for years before reaching Voyager 1's position, are still rippling through the interstellar medium like rings expanding from a stone dropped in water. Our sun, even from 25 billion kilometers away, is still shaping the environment Voyager 1 is traveling through. This is not chaos. This is a connected system. And Voyager 1 is documenting its behavior in real time. Now consider the logistical reality of what communicating with this spacecraft actually means in 2026. A signal sent from Earth travels at the speed of light, the fastest anything in the universe can move, and it still takes nearly 23.5 hours to reach Voyager 1. If engineers at JPL send a command to the spacecraft today, they will not receive a confirmation that it was received until nearly 2 days later. If something goes wrong in the meantime, there is nothing anyone can do. The spacecraft is completely on its own, operating autonomously, in a domain where human intervention operates on a 2-day delay. And that delay is growing. On November 18th, 2026, at precisely 2:16 in the morning Pacific time, Voyager 1 will reach a distance of 16,794,799,096 miles from Earth. At that exact moment, it will be 1 light day away from home. This means a radio signal, traveling at 300,000 kilometers per second, will take exactly 24 hours to reach the spacecraft. Voyager 1 will become the first human-made object in history to reach this distance. It will cross a threshold that no machine, no instrument, no piece of human engineering has ever crossed before. And here is what that number means in human terms. If you send a message to Voyager 1 on a Monday morning, you will receive its reply on Wednesday morning. If an instrument fails and requires an emergency response, the earliest that response can arrive is the following day. Mission controllers are not managing a spacecraft. They are corresponding with one. The relationship between humanity and Voyager 1 has transformed over 5 decades from command and control into something closer to a slow, patient conversation across an incomprehensible distance. What most people are not seeing is that this milestone is not just a number. It is a statement about where we are as a species. When Voyager 1 was launched in 1977, the concept of 1 light day away was purely theoretical, the province of astronomers and science fiction writers. Today, it is a real coordinate, and a spacecraft built by human hands is sitting at it, still functioning, still transmitting, still doing science. NASA engineers project that Voyager 1 will lose enough power to operate its remaining instruments sometime during the 2030s. The exact date is uncertain. It depends on how efficiently the team manages the spacecraft's diminishing electrical budget, and whether any unexpected failures occur before then. But the trajectory is clear. Within the next decade, the last instrument will go dark. The last transmission will be sent. And then, Voyager 1 will continue its journey in permanent silence, flying through the interstellar medium without telling us anything about what it finds, becoming simply an artifact, a bottle cast into the cosmic ocean that can no longer be heard. When that day comes, humanity will have no direct eyes, no direct ears, no direct instruments anywhere in interstellar space. We will go from having 2 probes in the space between stars to having none. And we currently have no replacement mission close to being ready to take their place. The Voyager program has given us something irreplaceable and irreproducible on any short timeline. Real, in situ, first-hand data from beyond the heliosphere. Not models, not simulations, not inferences from remote observation. Actual measurements taken by actual instruments sitting inside the actual interstellar medium. This data has revealed that our heliosphere is more complex, more dynamic, and more porous than we assumed. It has shown us that the boundary between our solar system and the galaxy is not a clean divide, but a messy, shifting zone where influences bleed across in both directions. It has detected plasma waves and density fluctuations in interstellar space that trace patterns of turbulence extending across astronomical units of distance, patterns that existed in no textbook before Voyager measured them. According to a landmark study published in Nature Astronomy, the Voyager 1 plasma wave system detected a class of extremely weak, persistent plasma wave emissions beginning around 2017. These emissions, sustained continuously across roughly 10 astronomical units of interstellar space, enabled scientists to map the density of interstellar plasma at an unprecedented resolution. What they found were density fluctuations, evidence of turbulence in the interstellar medium that no model had captured with this level of detail. This turbulence matters because it affects how cosmic rays travel through space, how the boundary of the heliosphere shifts and breathes over time, and ultimately, how protected our planet is from the high energy radiation that fills the galaxy. And here's the unsettling implication at the center of all of this. The heliosphere is our shield. It is the magnetic bubble generated by the sun that extends far beyond the orbit of Neptune and deflects the majority of galactic cosmic rays. High energy particles streaming in from supernovae and other violent events across the Milky Way before they can reach us. If that shield is more permeable than we thought, if its boundary is more complex and more variable than our models predicted, then the questions about how much cosmic radiation actually reaches the inner solar system and how that radiation level has changed over geological time become significantly more urgent. Because life on Earth evolved inside a shield whose characteristics we are only now beginning to understand. Voyager 1 is telling us, from 25 billion kilometers away, that we may not have had as clear a picture of our own cosmic environment as we believed. Now go back to those final images, the family portrait, the pale blue dot. They were captured from 6 billion kilometers away, which, in the scale of what Voyager 1 has since traveled, is laughably close to home. At the time those images were taken, Voyager had not yet crossed the termination shock, had not yet entered the heliosheath, had not yet approached the heliopause. It was still deep inside our solar system, and even from that relatively modest distance, Earth had shrunk to a fraction of a pixel. Carl Sagan, who fought for those images to be taken, who argued with institutional caution and bureaucratic risk aversion to make them happen, later wrote about what he saw in that photograph with a precision that has never been surpassed. He described every empire that had ever called itself eternal, every king who had ever believed his throne was the center of the universe, every war ever fought over territory. All of it contained within that 0.12 pixel speck, suspended in a beam of scattered light. His argument was simple and devastating. The photograph was proof that our collective arrogance has no justification, that our planet is not special in any way that the cosmos has bothered to acknowledge, that we are, in every measurable sense, inconsequential, and that this fact should make us more careful with each other, not less. That message was recorded in 1990. It has not yet been adequately received. But the photographs, as philosophically significant as they remain, are not the most important thing Voyager 1 has given us. The most important thing Voyager 1 has given us is the science it has been doing for the past 14 years. In the dark, beyond the cameras, beyond the images, in the space no human eye will ever see. Every piece of magnetometer data, every plasma wave detection, every cosmic ray measurement, every reading from instruments that most people have never heard of, returning data across a distance that takes nearly a day to cross at the speed of light. That is Voyager 1's true legacy. Not the photographs, the invisible work, and the people who receive that data, who process it, who publish it in journals and argue about its implications at conferences. Those are the scientists who went quiet when the images came back. Not because the images were beautiful, but because even those images, imperfect, grainy, philosophically heavy, represented the last moment that Voyager 1 looked back. Everything since has been forward, into the dark, into territory that no instrument built by any civilization on this planet had ever sampled directly. 49 years. That is how long Voyager 1 has been traveling. It was launched before most of the engineers who currently work on it were born. The people who built it have mostly retired or died. The technology it contains is so old that replacement parts no longer exist. When something breaks on Voyager 1, engineers do not order a replacement. They write code workarounds from the ground, transmit those workarounds across 25 billion kilometers, and wait nearly 2 days to find out if the fix worked. This is the level of commitment, patience, and ingenuity that has kept this spacecraft alive and functional for nearly half a century. In November 2023, Voyager 1 began transmitting garbled data, corrupted signals that made no sense to mission controllers. Engineers spent 5 months tracing the problem to a single faulty chip in one of the spacecraft's memory banks. From 24 billion kilometers away, they executed a software patch so precise that it redirected data transmission around the broken chip, rerouting it through functioning memory in a different location. The spacecraft began transmitting clean, coherent data again in April 2024. It was, by any reasonable definition, a miracle of engineering, performed across a distance that makes the word remote feel inadequate. And they know that the moment it goes quiet, a window that took 50 years to open will close and will not reopen in any of their lifetimes. By November 18th of this year, Voyager 1 will be one full light day from Earth. It will be traveling at approximately 61,000 kilometers per hour toward a point in the constellation Ophiuchus. In roughly 40,000 years, a time frame that makes the entirety of recorded human history seem like a brief Tuesday afternoon. It will pass within 1.7 light years of a faint red dwarf star called Gliese 445. Nobody alive today will know whether it does. Nobody alive in 100 generations will know, but the physics says it will happen. And somewhere on that spacecraft, attached to its frame, is a golden record, a 12-inch gold-plated copper disc carrying 115 analog images of Earth, spoken greetings in 55 languages, 90 minutes of music from civilizations across our planet, and etched instructions explaining how to build a device to play it. This golden record was not built for us. It was built for whoever finds it, in whatever corner of the galaxy Voyager 1 eventually drifts through, thousands or millions of years from now. It was an act of extraordinary optimism. The assumption that the universe is inhabited, that intelligence exists somewhere beyond our solar system, and that communication across interstellar distances and geological timescales is not only possible but worth attempting. And embedded in that optimism is a paradox that scientists and philosophers have wrestled with ever since. If Voyager 1 is our most ambitious message to the universe, it is also proof of how impossibly far away everything is. The nearest star to our sun is over 4 light years away. Voyager 1 would take approximately 75,000 years to reach it at its current speed. The distances involved are not large. They are not vast. They are incomprehensible in a way that the human brain was not built to process. And yet humanity built this machine, launched it with the technology available in 1977, and it is still out there, still talking to us, still doing science that changes what we know. What will the data from Voyager 1's final years of operation reveal about the structure of the interstellar medium? Will the magnetic field measurements confirm the theoretical models being rebuilt in the wake of what the heliopause crossing exposed? Will the plasma wave instruments detect something that further challenges what we believe about the space between stars? And when the last transmission finally goes silent, when that faint whisper traveling 25 billion kilometers finally stops, what will we have learned, and what will we still not know? More urgently, what comes next? There is currently no approved, funded mission designed to follow Voyager 1 into interstellar space. Proposals have been discussed. The concept of an interstellar probe has been studied by NASA, with preliminary analyses suggesting a mission capable of reaching the heliopause in roughly 15 years, rather than the 35 it took Voyager. But a concept is not a mission. A study is not a spacecraft. And the political and budgetary realities of deep space exploration mean that the gap between Voyager's silence and any successor's arrival in interstellar space could span an entire generation or more. We may be living through the only window in human history, so far, when direct measurements from interstellar space are possible. And that window is closing. When Voyager 1 took those final images in 1990 and left scientists speechless, it was not because the images themselves were beyond anything anyone had seen. It was because those images forced a confrontation with something true and uncomfortable, that from the perspective of the cosmos, we are infinitely small. That every problem we have collectively decided is important is happening on a speck of dust orbiting a minor star at the edge of an ordinary galaxy, in a universe so large that the numbers describing its scale have no human meaning. And yet, here we are, building machines, launching them into the dark, listening for their whispers across billions of kilometers of empty space, refusing to stop. That refusal to stop, that stubborn, irrational, deeply human insistence on reaching further, measuring more, understanding better, is perhaps the only thing about us that the cosmos might someday find remarkable. Voyager 1 is still out there, still moving, still transmitting, still telling us things we do not fully understand, and somewhere in the data still coming back, in the magnetic field readings and plasma wave detections and cosmic ray measurements arriving across a distance that takes nearly a day to cross at the speed of light, there may be answers to questions we have not yet thought to ask. Or there may be something else entirely. Something that, when we finally understand it, will leave us speechless again. The question is not whether Voyager 1 has more to tell us. The question is whether we will still be listening when it does.